And, look, I said this is the volume of one energy state. But even for electrons, how many electrons can you have in one energy state?
One number.
Not just one. So think about it. So this electron has quantum numbers nx, ny, and nz. I have an electron with nx, ny, and nz. Can I put in another electron? Say it's n1, 2, and 3. I have 1, 2, and 3 quantum numbers here. Can I bring in another electron up that has quantum numbers 1, 2, and 3?
Yes.
Absolutely not. I have two spin ups. Right, so I can't do that.
We can put in a spin down.
But I can put in a spin down with quantum numbers 1, 2, and 3 because then it's spin half, but then ms minus a half.
You got.
So I can have 2. So check this out. Let's say what we want to do over here is we don't want to fit one electron. Let's fit nq electrons. So now fit nq over 2 electrons. And I do the 2 because I'm going to have 2 electrons in every state. So if over here I have nq over 2 electrons times the volume that each of the 2 takes, this is the total volume that I need, right? This is the total volume of electrons that I'm filling up.
Yep.
And so over here what I do is instead of writing just the k, I write 1/8 4/3 pi and k Fermi cubed. Where now this k is essentially the radius to fill up that encompasses one electron state. Okay, now this k Fermi is the energy that encompasses all the electrons. Okay?
This is just for one electron outer shell.
So what this approximation is however many electrons in an outer shell.
Because you're saying n times q, but n is the number of atoms. If you had 20 electrons in each atom.
Right. Q is the number of free electrons per atom.
Oh, all right.
Yeah.
I thought you just meant free electrons.
Okay. So it's the total.
Each atom can have the same energy state, but at any point you're going to see 2 of those electrons for that single atom. Each individual atom can have the same energy state, but each atom can only have up to 2 electrons in that particular energy state.
Okay, so what we're talking about, we're blowing together a lot of things. We're kind of thinking towards a metal. And the way the metal bonds is that you have these core electrons which are held tightly close to the atom. And then you have valence electrons. Right? And those valence electrons, the way the metallic bond works, are essentially completely free to roam around the whole atom. So these electrons, we're not talking about being bound to any particular atom anymore.
Okay.
We're talking about the free electron gas. A metal, those electrons that flow in a metal are considered a free electron gas. They're not bound to anything. They're just quasi-free, quasi-there inside of a box.
So they're not actually attached to any
box is the
particular
metal.
nucleus,
They're not attached to anything at all.
Right, and the box in this case is the slab of metal,
That's right.
and the electrons could be in here.
That's right.
Okay.
Okay? Okay. So now let's do a little magic here. If you solve for k Fermi over here, you end up with k Fermi equals, well, let's do this. Another little magic we defined. Rho is defined as nq over volume. And what should that be? That's the density of electrons, right? That's simply the density of electrons equal the electron density. It's the free electron density, right? The valence, the free electron density. All right, and so if you substitute that into there, you get k Fermi equals 3 rho pi squared to the 1/3. So essentially that's the Fermi wave number. Okay, and now here's the big kicker. Remember, E total, Now in these spherical coordinates, remember E total was h bar squared over 2m times kx squared plus ky squared plus kz squared. Now we're in spherical coordinates.
So it would just be,
So it's, I think, I remember seeing that this is h bar squared over 2m kf squared. So that's the total energy. All right, and in this case, this would equal, let me see if it works. It equals h bar squared over 2m. Yeah, this is right. Yeah. So it's h bar squared over 2m k Fermi squared, which is 3 rho pi squared to the 2/3. Okay, so this is a huge result. And what I love about this result is the simplicity. What do you need to know to calculate the Fermi energy?
just the density of.
The density of electrons, the free of electrons. That's it. Isn't that beautiful? Yeah, just grow. Okay, but what does E Fermi mean? Okay,
It's
think
the
about it.
same E Fermi.
What's that?
It's the same.
This is the same E Fermi.
From semiconductors?
Yep.
Okay.
And essentially that's the same Fermi as this.
Right.
Yeah.
So it's the energy level that will cause that the electrons or the Fermi transition at. Transition level for the.
So how about this? We took into account that the Pauli exclusion principle, that you can't squish them all together into the same state, right? So then what we start doing is we start chunking them in there and packing them in there. Fill this state, go to the next state, fill that state. Did we have any gaps in there? Like did we fill, for this discussion, did we fill this end and then skip this end and then go to the next end?
No, you fill them.
We filled each.
What we did is we
individual-
chunked it all together.
We filled every single one of them.
We try to get the lower energies first.
Right. And we filled it up. So in other words, the Fermi energy is the highest energy from which if you stacked all the electrons into their lowest energy states, below E Fermi, you'd be completely filled up. And then above E Fermi, it'd be nothing. So essentially, E Fermi is the energy below which you've packed everything as closely together as you can. All right, and we took into account the Pauli exclusion principle completely there by only allowing, particles, 2 particles per state, a spin up and a spin down. All right, and so I think that's a very cool result. So look, in general, the only time you have that is if your system is very cold, because if you have a little temperature and a little bit of energy, electrons are essentially popping out of the Fermi, right? They're pumping up, they can go to the next level state or something like that. Right.
Get
But-
excited.
And so the idea is that the Fermi energy is that if you could get things at absolute zero, this would be exactly true. You can't get to exactly zero anyway, but that's what you'd have. You'd have this shell of stuff that's fixed. But here's the scoop. Under normal conditions, and I'd like you to go back to problem on page 23. So do this for homework on page 23, problem 1.18. All right? They talk about what is cold. All right? So when things are cold, the Fermi energy is going to be this highest energy state. And it turns out room temperature for metal is very cold. So to a good approximation, the Fermi energy level of whatever the solid is that you're working with is a very good estimation of how filled the electrons are in that metal. They're filled up to that energy level state. All right? And so that's why when you make a thermocouple, you bring together 2 dissimilar metals. Here's one metal. Here's metal A. And its Fermi energy might be up to here, right? And then another Fermi, E Fermi A, and then you have another metal whose Fermi energy is right here. you bring those together, right? And then electrons are going to try to, these are essentially at a higher energy than these and these, so these electrons will come over here. And when these electrons fill up over here, it will make this all negative, it will make this side negative. And then when they're gone over here, it makes this side positive. And when this side is positive and that side's negative, you have a potential difference between them.
And they can heat up due to the
Okay,
resistance.
and then it turns out as a function of temperature, the distributions change. Okay? Okay, so this is a great example. If you follow through in the next section, they calculate the total energy that's inside this Fermi shell. And what they do is they show that if the shell expands, then the total energy of the system gets smaller, all right, which means that it did work on the outside. And it also shows that if you were somehow tried to push, right, to make this smaller, to push the Fermi energy in, that it requires external energy, all right? And so this is kind of the reason why atoms don't collapse. Because if you have your Fermi shell like this, right, all by itself, it's not going to push in and collapse to zero. You would have to have external pressure to collapse it. And even then you couldn't do it. And that's what they call the degeneracy pressure. All right, and so they talk about a couple examples. There's some nice homework problems there that I want you to do. All right, and there's really, I'm only going to cover the band structure, the next section, and not in great detail in this chapter, and then we'll go to perturbation theory, okay?
Student 5.4.
Yeah, we can't do it, all right? What I do want you to also do is the following. Is that in terms of the Fermi energy, remember I talked about the three distributions that you could have, the classical distribution and then the Maxwell-Boltzmann?
Page 241.
Yep, so page 241, all right? Page 241 gives the following, n of epsilon equals, so it's e to the minus epsilon minus mu over kBt, and then we have 1 over e to the minus epsilon minus mu over kBt plus 1, and then 1 over e to the minus epsilon minus mu over kBt, and that's minus 1 for bosons. So this is classical, this is fermions, and this is bosons. And n is the probability of finding a particle, sorry about this, particle with energy epsilon versus epsilon. Right, so in other words, it's n of epsilon versus epsilon, all right? And mu is called the chemical potential, and it's a function of temperature, and it equals minus alpha kBt. And here's the scoop, mu of T equals 0 equals E Fermi. All right, so what I would like you to try to do is plot this. So let's, instead of writing mu, let's write E Fermi. All right, and I'd like you to plot these. I'd like you to plot these three. All right, and so look, you don't have to put everything in. You can do it generically. There's some number like x minus E Fermi and just make up an E Fermi. And then play around with the temperature. It's more complicated than that. But I'd like you to replace the mu by E Fermi and then put in different temperatures here. and see what happens to these distributions as the temperatures change. All right, I did this in Maxima, and it came out very easy, all right? And I think I put it in Modern. So what I can do is I can put up this file for this class so that you can have a look at it.
You had us do it last semester.
Yeah, but in Modern, yeah. Okay, so what I'll do is I'll discuss that when we come back next time. Okay, so your homework assignment is to continue working on those homework assignments in this chapter, which you should have a much better feel for now. And here's the scoop. I am also going to put up the homework solutions for, you ready? 5.4.5. Oh, no, that's section 5.4. So look over section 5.4.5. And then I'm going to put up the homework solutions for 5.35 and 5.36. And those are triple starred problems. All right? So I'm not going to ask you to turn those in. But if anybody's doing astrophysics, the first problem is on white dwarfs. Remember, if we replace that electron gas. Remember, so here's something I didn't emphasize. That structure, the Fermi energy, didn't have anything to do with the electron-electron repulsion. Right? Did I include that in the free electron gas model? Not at all. It's not even there. So just by virtue of, the Pauli exclusion principle and, quantum mechanics, we force this to have that pressure, right? That structure. And so that's what holds up a dwarf star. And also 536 is a neutron star and the Cassandra limit and stuff like that. So I'm not requiring you to hand in problems 5.35 or 5.36, but I'll post them so that you guys should look at them, all right? But do the other ones that I asked you to do. And then we're going to do perturbation theory, and we are going to do perturbation theory quickly. We might not do the atomic physics. And so here's the scoop, is that we want to do perturbation theory, variational calculation, and the WKB approximation. And then I want to quit this book. Maybe do scattering. Okay? And so the problem is that I'm not going to address any of those problems, any of the things. Like in perturbation theory, they get into a lot of very nice atomic structure, like atoms in magnetic fields and electric fields, and we won't be doing that, all right? We might get to it in Townsend. Yeah.
We do quantum 3, you do quantum 3 next semester, we're going to that stuff then?
Well, so quantum 3 I try to keep right now as like particle physics,
Okay.
all right? And so quantum 3 is particle physics. What I would like to do is, if you guys want it, is do an outright atomic physics course. And the outright atomic physics course has more of the flavor of what we did for the helium, and then going into that full atomic structure. Now, you also get that the electrons in an electric field and a magnetic field, you get a flavor of that from experimental. Because when you look at experimental, you look at the perturbation theory, and you look at the fine structure, the hyperfine structure. So you do have it all together, all right? Okay? All right, good, thanks guys. So hand in those homeworks though for Monday from the chapter 5. No, Tuesday.
Yeah.
Yeah, I know, I'm surprised Professor Arn isn't here.
Yeah.
I had a question.
Yeah.
In a conductor, don't you usually have most electrons on the outer shell on the outer surface?
Conductors?
Yeah.
Yeah. So that's what we're talking about here.
So aren't these all going to push out to the other surface? They're not going to stay in the center.
So what we
Free
have
electrons.
is that, so in other words, if you calculated the Fermi energy of a conductor, right,
Yeah.
that would be essentially the energy that you would need to ionize an electron from the metal. Yeah.
Was anyone going to do it?
No, but I want chapter 5 homeworks have to be done by Tuesday. And there were a whole bunch of them.
Yeah.
All right? And they will all require you to look in the solutions. None of them are trivial. Okay, what was the conclusion of these?